So week 6 starts off on a new topic, the topic of Fourier analysis of continuous time signals, and that's what we're going to be covering today. So and of course we plan for the cut 1. So the first thing we are going to look at is the introduction, and then Fourier series representation of periodic signals. As a way of introduction, we are going to mention that we have already covered, or you have already covered, the Laplace transform in the unit circuit and network theory 2. I presume you have already done that. It was adequately covered. And I also figured out that you are going to be covering the Z transforms in a unit in 5th year called digital signal processing. If you have not already covered a little of it already, these are transforms that are very useful in converting time domain signals into S domain, that is the one that is achieved by Laplace, and Z domain that is achieved by Z transforms. And for many purposes, they are more convenient to analyze and process, particularly when you are dealing with continuous time signals. In addition, greater insights into the nature and the properties of many signals and systems are provided by this transformation. So we are more likely to understand how a signal or a system behaves when we analyze it in the Laplace or Z transforms. Now, in this chapter and the following one, of course, the following one we are not going to be dwelling much because it deals with discrete time, and those concepts are dealt with in another unit. So for this chapter, we shall introduce the Fourier transforms and the Fourier series, which convert time domain signals into frequency domain representations, which are also called the spectral representations. And so in addition to providing spectral representation of signals, the Fourier analysis is very essential for describing certain types of systems and their properties in the frequency domain. So in this chapter, we shall introduce the Fourier analysis in the context of continuous time systems. And as I mentioned, the discrete time representation of Fourier transforms is covered in this unit under the title Discrete Fourier Transforms. To start us off, we look at the Fourier series representation of periodic signals, and we just remind ourselves of the periodic signals that we looked at in chapter 1, where we defined a continuous time signal xt to be periodic if there is a positive non-zero value of t for which this equation 5.1 is satisfied for all t. And we also said that the fundamental period t naught of this function xt is the smallest positive value of t for which this equation is satisfied. Further, we said that we can define the fundamental frequency as the reciprocal of the fundamental period. And now we say that the two basic examples of the periodic signals are: one, the real sinusoidal signal that may be represented by equation 5.2, and number two, the complex exponential signal that is represented by equation 5.3. What we notice about these two basic examples of periodic signals is that we are always able to determine their fundamental angular frequency, omega naught, to be equivalent to 2 pi over t naught. It is also equals to 2 pi the fundamental frequency f naught. And now we delve into the Fourier series representation. And we say now that the complex exponential Fourier series representation of a periodic signal xt of fundamental period t naught is defined by equation 5,4, and this says that xt, or our periodic signal xt, may be represented by a sum of ck exponent of jk omega naught t, and still we keep our omega naught as we defined it earlier. The only new term that we are introducing is the ck, and ck is known as the complex Fourier coefficient and is defined by equation 5,5, which is the integral over any one period. So this symbol represents the integral over any one period. And of course, we are starting with the reciprocal of the period, so that the integral cancels out with this reciprocal. And therefore, we are saying that ck is the integral of xt over the period defined, and then we multiply with this exponent. So if from this equation 5,6, if we set k to be equals to 0, this terms goes, and you are left with c naught to be 1 over t naught and the integral of xt over the period of the integration. And therefore, what we are saying now is that c naught, as we can see, equals the average value of xt over a period. And when xt is real, then equation 5,5 follows that minus ck is equals to the complex conjugate of ck. And you see these things when we start doing the examples. So another way in which we can define the Fourier series for a periodic signal is trigonometric form. And we have already done exponential or complex exponential form. And therefore, this is a special way in which you can the complex exponential form can be expressed as or in trigonometric form. And we say now that trigonometric Fourier series of representation of a periodic signal having the fundamental period t naught may be expressed as in equation 5,8. And this is pretty much the same way we did the complex exponential, except that we are breaking up our complex exponential and into, or using the Euler's formula. And we are able to have two trigonometric forms, the cosine and the sine. And so if we just take it as such, then we are saying that the definition of our periodic function xt may be expressed as a constant and the sum of periodic or trigonometric the trigonometric functions that are expressed as sine and cosine, and each of them has a Fourier coefficient ak and bk. And we are saying that now the bk and ak Fourier coefficients that may be defined, and we have deliberately avoided the derivations of this. It can actually be done, but for the sake of time, we can just accept that if we define our Fourier representation of a periodic signal as in 5,8, then we can say that the coefficients may be defined as that. And again, the only thing we are doing is that this is twice the the integral over the period. So if you remember that we are saying ck is 1 over t naught integral of over one period of e x j omega naught kt. Of course, the x of t is there and dt. Therefore, if we remember that is how we were doing it, then we are saying that as a matter of fact, the Euler's function normally introduces a half when you break the complex exponential to the sum of the cosine and sine. And therefore, that reason we can simply see that we are introducing now a 2 to cancel out this a half sign that is normally introduced by the Euler's formula. And if we take it as such, therefore, then we can say that this coefficient AK makes sense, and it takes the cosine term, and the BK takes the sine term as expressed by these two equations. And we are saying that the AK and BK and the complex Fourier coefficient CK, of course, can be related as I have just alluded to earlier, that the C naught is going to be half of A naught, and therefore this is the half, the 2 that is being cancelled by these 2, and for that reason we are able to express C naught in terms of A naught. And the AK may be expressed as a sum of CK and C minus K, and as simply as we can see in equation 5.10. And in a similar manner, without going into the derivations, we may express CK in terms of AK and BK, and you can see now this is a complex Fourier coefficient. It has a real term and the imaginary term BK, and for that reason, that equation 5.11 holds, and we are saying that CK is twice the real part of CK, and BK is twice the imaginary part of CK. And now let's talk briefly about the even and odd signals and how they are get represented when we transform them to Fourier series. And you're saying that if a periodic signal xt is even, then this term, of course, will be 0 because it's imaginary. And that is exactly what it means. And we see now that the Fourier series that is represented in equation 5.8 only contain, the 5.8 is right here. We drop this term because you're saying that we know by default that cosine is even, cosine function is always even, and the sine term is always, or the sine function is odd, and therefore, since we were saying that our function is even, xt is even, then we are saying that we are going to drop this term, and we are only going to be left with the cosine term, which is even. And therefore, we can, our equation 5.8 takes this form. And on the other hand, if the our function xt is odd, then our ak, which is our coefficient of the cosine term, goes to 0, and we are left with the sine term, as you can see in equation 5.14. We have another way in which Fourier series representation may be accomplished for a real periodic signal, and we are saying that the other way is called harmonic form of Fourier series, and the harmonic form may be expressed as in equation 5.15, and equation 5.15 states that a real periodic signal xt may be expressed as a constant C naught and a summation of ck cos k omega naught t minus omega theta k, and the omega naught remains the same value of 2 pi over t naught. And you're saying that this equation 5.18 is easily derived from equation 5.8, which we already met, the trigonometric representation of Fourier series. We don't have to go through the derivation, but we are saying that this equation 5.15 is known as the harmonic form of Fourier series. So this equation is harmonic form, and we are saying that the term C naught is known as the DC component, or the constant component, and the term ck inside the summation sign is considered or called a kth harmonic component of xt. So you might have the first harmonic component of xt, second harmonic, or nth harmonic, or sorry, rather kth harmonic of component of x of t. And you know, the first harmonic component with the C1 cos omega naught t minus zeta 1 is also referred to as the fundamental component because it has the same fundamental period as that of our real periodic signal x of t, and the coefficient ck and the Argos zeta k are referred to as the harmonic amplitudes and harmonic phase angles. So when we are saying this is harmonic phase angle, so we might have the first harmonic phase angle, the second harmonic phase angle, etc. And similarly, we are saying that the ck is considered as the harmonic amplitude. So we might have the first harmonic amplitude, second harmonic amplitude, etc. And those terms are going to come in quite prominently when we start doing mathematical problems that you might be told that find the second harmonic amplitude of a signal expressed by of a real signal x of t, and therefore we should be able to do that. So we are saying that they are also referred to as the Fourier coefficients ak and bk. Of course, we're saying that they are related to the Fourier coefficients that we defined earlier, ck and bk, and we can say that c naught is taking the same value like we have mentioned before, and therefore the ck may be expressed as bk or ak squared plus bk squared root, and similarly tan of theta, tan inverse of bk over ak will give you the kth harmonic phase angle, as expressed in equation 516. Now, to sum it up about harmonic form of Fourier series, we mentioned that for a real periodic signal x of t, the Fourier series in terms of a complex exponential as given in 5.4, we were able to define the complex exponential form of Fourier series, and have tried to reintroduce that equation here there, where we have this is our periodic signal. It is expressed as this expression at that point, and we are defining our ck as this term, and therefore we are saying that this is the most commonly used form of Fourier series representation, and therefore the other two, of course, it is equivalent to the 5.8 and the 5.15, as we have seen, the harmonic form and the trigonometric form, but he's saying that the complex exponential form is the most general and the most common that we are going to be using most exclusively. When Fourier defined the Fourier series representation of periodic signals, the only condition that he set, or the sufficient condition, was that the signal has to be periodic for it to be representable using the Fourier series. But then there were problems because when people tried to do the representation of some signals, they made some problems. But now this gentleman called Dirichlet established the exact conditions that are necessary, or rather that are sufficient for a signal to be represented using Fourier series. And the three conditions are listed here. The first condition is that the function xt that is periodic, first of all, of course, it must satisfy the requirement of periodicity. So once that condition is met, we are saying that there are three other conditions that must be met for the signal to be representable using Fourier series. And they're saying that the first condition is that the function x of t must be absolutely integrable over any period. And for that reason, we are saying that that means that if you integrate your function of x of t, or the absolute value of your function x of t, must always give you a value that is finite or that is less than infinity. The second condition is that the x of t must have a finite number of maximas or minimas within any finite interval of t. And lastly, x of t has a finite number of discontinuities within any finite interval t, and each of these discontinuities must be finite. So we also say that these are the sufficient conditions that allow you to do the representation of a periodic signal, but then they are not the necessary conditions, and those necessary conditions may be found out in problem 5.4, and I will endeavor to look at it particularly when you are doing the revision of the problems at a later section, particularly during a tutorial. Amplitude and phase, amplitude and phase spectra of a periodic signal are quite significant, and we should get to know them. And if we have the Fourier series representation of a periodic signal, we can always be able to define or derive the amplitude spectra and phase spectra from the Fourier or complex Fourier series coefficient Ck. So assume we have Ck defined as we remember how we defined Ck. We said Ck is equals to, from k is equals to 0 to infinity x. Sorry, that is definitely not how we defined Ck. We said Ck is 1 over t naught integral of the period of x of t being our periodic signal, then minus j k omega naught t dt. Now, if we know our Ck to be that, and then we are saying we can express it as such, from this Ck, we are saying that a plot of Ck magnitude. So if we get the magnitude of this, this gives us Ck magnitude versus the frequency, which is omega. So if we now do a plot of Ck magnitude again over the frequency omega, we are saying that the plot of this is called the amplitude spectrum of the periodic signal x of t, and a plot of phi of k is of course this term. There is an angle component or angular component that is defined as phi of k. If you plot that versus again the omega, then you are going to end up with the phase spectrum of x of t. And since k assumes only, this assumes integer values as by definition, the amplitude and both amplitude and the phase spectra are not going to be continuous in frequency, and they will only appear at discrete frequencies as defined by omega naught, k omega naught. Therefore, they are referred to as the discrete frequency spectra or Rhine spectra. And of course, we know by definition that C minus K is equals to C of K, a magnitude, and the phi minus K is going to be equal to negative of phi of k. And from that statement that we have already made before, we can say that the amplitude spectra, which is defined by the magnitude of ck, is going to be an even function, and the phase spectra that is defined by phi of k as a function of omega is going to be defined, is going to be considered, or is going to be realized as an odd function of real periodic signal. So here, before we talk about the power content of periodic signal, I have added some example that illustrates the concept of phase spectra and amplitude spectra. I'm not going to spend much time on this one. You can look at it on your own. But the example is simply telling you that if you consider this rectangular pulse train defined as in this figure, the first question you are asked to do is to find the Fourier series coefficients, aka, bk, and a0 over 2, which of course are derived from ck is considered to be ak in our definition plus j bk. So if we know that to be the case, we can always be able to find ak and bk from our earlier definitions. And the first, when k is equal to 0, that is going to be a0. So we are saying that you find out that, and this is done, even the solution is right here. But I just want to show you what we mean by the amplitude and phase spectra, because that is the next task that this example requires one to perform. And this is done by obtain mk. Mk is equivalent to our ck, because that is what we said. We said ck magnitude is equals to ak squared plus bk squared square root. So of course this is the same symbol. It's only that using different text you find them using different symbols. And we are saying for us to plot the amplitude spectra, we require the ck magnitude, and it is obtained as this one. And therefore, you plot against omega. And to plot the phase spectrum, we need to determine, to find phi. Remember, again, we are using different text. We define phi of k to be tan inverse of bk over ak. If you remember in our notes, we already have found that to be the case. So we are able to find that, and then you plot it against the omega. And when you do that, you can use MATLAB, and you have explained that you can use the STEM program instead of the plot. And here are the plots of the amplitude, which is plotted ck as is our amplitude, and phase is plotted here, phi of k. And therefore you can see that they are not discontinuous. They are only appearing at finite times when k is defined for our periodic signal. So for I think I would ask you to perform this task. And if I just go through this, I may not have shared this, but I am going to share this two pages or the entire example. But even if you post this video and look at the example, the solution that I have indicated, you can definitely be able to do that problem, and even on MATLAB. So that is it for about the amplitude spectrum and phase spectrum. We, of course, needed to be able to determine the power content of a periodic signal. And to do that, we are mentioning a problem 1.8 that is found in chapter 1 of our notes. And in that problem, you actually get introduced to the concept of average power of a periodic signal x of t. And it can be found to be defined by equation 520. So we don't have to go there. And we can say that over any period, power of a periodic signal can be evaluated as 1 over period t0 multiplied by the integral over the entire period, or with respect to time. And this equation 520, if you now know that we can be able to express the x of t as a function of or in the complex exponential Fourier series form that we define by sum of ck ej k omega naught t for k is equals to 0 to infinity. Therefore, we can say that if you are to get the amplitude or the magnitude of this term, you are going to realize that though this term is going to become a 1, and the only term that you are going to find is ck modulus, or the sum of ck modulus from minus infinity to 0. So in that being the case, therefore, we are saying that we can be able to express average power of a periodic signal as equivalent to the sum of the complex exponential coefficient ck squared. So I guess that makes the point, and what you needed to get used to or to understand is this identity that was derived or defined by Parseval, and it is called, this definition is called Parseval's theorem for Fourier series.